You cannot split it. How come? Because this limit is not a number. You cannot say limit of this minus limit of that. No, because this is not a number. What is the limit of 1 over x as x approaches 0 from the right? Anyone?
Here.
Okay, if you remember the graph, you will never have a problem with this. Here's the graph of 1 over x.
Infinity.
Yes, it's right here. As x approaches 0 from the right, the function values go to infinity. And I don't even care what this one is doing. If this one is infinity, then I cannot split it. So that won't work. What will work then? What is our only option here? We only have one option to proceed. Yes, if you remember, I said we always plug it in, but very rare situations, or I shouldn't say very, but in low percentage, I can't. I have to do something else before I plug it in. What can be done here, you think? And it's the only thing that I can do. What can you do? What is the only option to proceed? What do you think?
So I'll say simplify, but do that by making the denominators the same.
Exactly. Finding the least common denominator. There is nothing else. Absolutely. It's the only option. Awesome. So what is the least common denominator? Let me look again if I copied this correctly. Is it e to the, where is it? E to the x minus 1. So just to make sure it's not power, e to the x and then minus 1. Just to make sure it's very clear. Good. So then what is the least common denominator then?
X e to the x minus x.
Very good. Product of these two. So then this one needs an e to the x minus 1, and then this one needs an x. So this is e to the x minus 1 minus x. Now I can plug it in. What do you hope for when you plug it in? Before you plug it in, what do you hope for? What do we always hope for?
Infinity, or
exactly. Yes. Which one is it?
0 over 0.
0 over 0. So this is 1. 1 minus 1 is 0. Minus 0 is 0. This is 0. I don't care what I have here, but I do have 1 minus 1, which is 0. Awesome. So we are in business then. But don't get stumped by this. That's the only way to continue. Good, page 12. Okay, so then I will just distribute here and then apply L'Hopital's rule. As x approaches 0 from the right, e to the x minus 1 minus x, x e to the x minus x. Good. So it's 0 over 0. So can anyone differentiate the top for us?
e to the x minus 1.
Perfect. Now the denominator, be very careful. This is a product. If you don't apply the product rule, that will be wrong. So the first function prime is 1 minus the first function times the second one prime and minus 1. Okay, good. Next.
Why is it minus?
When I differentiate negative x, I get negative.
e to the x.
Oh, yeah. So, sorry. Thank you. No reason. Thank you very much. My mistake. My apologies. First function prime is 1 times the second one plus the first one times the second one prime. Yeah, I was looking already here. No excuse. Okay, so the top is again 0. The denominator is, again, this is 0 and this is 1 minus 1, which is 0. We continue. Limit as x approaches 0 from the right. So the top prime is just e to the x. The denominator prime is e to the x plus first function prime is 1 e to the x plus x e to the x. And this prime is 0. Now we have to be careful and factor out. What will I factor out in the denominator? So actually, because the numerator is no longer 0, I was going to simplify, but let's just look at this. So e to the x, when x approaches 0, the numerator is 1. E to the x, when x approaches 0, this is 1, and this is 1, but this is 0. And this is done. We don't have to do anything else.
Professor?
Yes.
I kind of got lost at the last step when you applied the rule again.
From here?
Yes.
Okay, so let's do that again. So e to the x prime is e to the x. Negative 1 prime is 0. E to the x prime is e to the x. X e to the x prime, the first function prime is 1 times e to the x plus x times e to the x prime. Negative 1 prime is 0. As x approaches 0 from the right, this approaches 1. This approaches 1, this approaches 1, but this approaches 0 because this is 0 in front. So 1, 1, 1. 1 over 2.
Thank you.
Is that okay?
Yes.
Perfect. Okay, what are we practicing next? Can we consider Newton's method done?
Could we go over one problem from
Yes,
there?
yes. Please choose any Newton's method. And this is in 4.8. Sorry about that. It's off. Okay, so let's look at the Newton's method. Am I in 4.8? Yes, I am. Okay. Anything you like to choose?
Yes. Can we do the...
We did 20 last time.
Did we do 21?
Yes, let's do 21. Perfect.
Yes.
So in 21, we have arc tangent x equals x squared minus 3. You understand that no one can solve this problem, this equation, by hand, algebraically. There is no way.
Yeah.
Perfect. So then the first thing, I move everything to one side because I need to identify my function. So this is my function f of x arc tangent x minus x squared plus 3. I have to immediately have arc tangent, the function differentiated, 1 over 1 plus x squared minus 2x. I have to have, at some point in time, this written out, because this is what I am going to enter in the graphing calculator. So I have these, but I don't have the interval yet. I don't have the initial value yet. So now I'm going to put in the graphing calculator just a function. So I'm going to share my screen. Okay, in y equals clear. And I only put in arctangent, which is tangent inverse of x, and then minus x squared, and then plus 3. And I only hope, first of all, the mode has to be in radian mode, and I only hope that I don't have to run around about, finding an interval too high up or too low in the negative. So let's try. I'll start with 0 and see what happens. I'll continue to 1. Promising. I'll continue with 2. I'll continue with 3. Got it. Between 2 and 3. So the interval is 2, 3. And I have f of 2 is positive and f of 3 is negative. Good. So I would say f of x continuous on 2, 3 as a sum or difference of continuous functions by, and this is a second hypothesis. This is number 1, and number 2 I already wrote here. By IVT, not MVT, from 1 and 2, I will find a C in the open interval 2, 3 such that f of C is 0. There is no derivative here in IVT. Okay. So what I'm going to do now, I'm going to enter this function. It doesn't matter where I start, but I have to make sure that when I look at the first derivative, if I start with 2 and I get 0, then I can't start with 2. If I want to start with 3 and I get 0 in the denominator, I cannot start with 3. So let's see what we have. So 2 squared is 4. So 1 over 5 minus 4 is not 0. 1 over 5 minus 4 is not 0 when I plugged in 2. 1 over 5 minus 4, not 0. So I will consider my starting point 2. So then I go back to the graphing calculator. Do not delete what you have in there because it's so difficult sometimes with these functions to even put them in. Do not delete. Just go with second and insert. So put in the x, put the minus, put parentheses because everything in the numerator has to be in parentheses. Close, divide, again parentheses, and be careful how you enter the rest. Very important. 1 divided by, if you don't put parentheses around 1 plus x squared, you're not going to get anywhere. And then minus 2x. And then close parentheses. And now get out of there, go to variables, call variable y1, put inside 2, and this is our first iteration. Yes, as you see, it jumps out of that interval, but that's okay, as long as it eventually will stabilize. So our x1 is 2.028197031. And now this is the only change. I overwrite 2 and I make sure that I inserted the previous answer. And doing that all the time, it will plug in the previous answer all the time. So our x sub 2, 2.027974792. And now I don't have to change anything. So x sub 3. Oh, yeah, and the solution is between 2 and 3. Oh, we're all set. Sorry. So I don't have to copy this. The method already converged. As you see, 1, 2, 3, 4, 5, 6, 7 decimal digits. I will not copy the next one. So it converged in 2 steps. Okay? So this is it. So 2, 4, 6. I don't need the third one because the third one has the same digits, more than 6. So this problem, once you understand it, it should take just a couple of minutes. Any questions on this? Any questions on this?
No.
Perfect. You have that video just in case. So let's look at the list. We looked at graphs, we looked at L'Hopital's rule, Newton's method, optimization, mean value theorem, Let's also look at again at the closed interval, because this is another important information. The critical numbers are almost in everything we discussed here, except Newton's method. So let's go back to, I think that it was 4.1.